Hi, in this video, I'm going to do problems from section 2.4, which is linear and nonlinear equations. Okay, first of all, I'm going to talk about the existence and uniqueness of the solution. As I mentioned in the first or second video, what I mentioned there is not all differential equations are solvable. Okay, there are some differential equations that are not solvable, or meaning that the solution do not exist. Okay, so some differential equation, the solution exists, but they are very hard to solve. Okay, that's why we need the qualitative solution. So you draw the phase portrait and then try to see how does the solution look like. Okay, so but what is the condition that a differential equation has solution in an interval? That is the thing that we are curious about. Do all the differential equation have solution, or the solution of all differential equation exist? No. So there are some conditions that a differential equation must satisfy in order to have solution in an interval. Okay, so this video is all about that. So we will discuss about the existence and uniqueness, meaning is there a solution exist? If yes, is it unique? Okay, that those kind of things we will be discussing here. Okay, so first of all, let us talk about the linear differential equation. Okay, so in case of the linear differential equation, what happens? Theorem 2.4.1, this is the same theorem from the book. If the function pt and qt, look at this differential equation here. Okay, so pt is the coefficient of y and qt is the function of t on the right hand side. Okay, if the function pt and qt are continuous on an open interval I equals to alpha and beta, so this is an arbitrary open interval. So if the function pt, this function, and qt are continuous in that interval, and such that this interval contains t equals to t sub 0. Okay, this must contain, because the function may be continuous in several pieces of interval, but the uniqueness and existence of the solution of this differential equation is guaranteed on that interval that contains t equals to t0. Okay, then there exists a unique function y equals to phi t that satisfy the linear differential equation dy over dt plus pty equals to qt. So if, since the initial condition is given t equals to t0, there will be only one such interval that contains that point, and then the solution satisfy this equation. Okay, for each t in the interval I, and also satisfy the initial condition y at t0 equals to y sub 0, where y sub 0 is an arbitrary prescribed initial value. Do you remember that in the last videos we discussed briefly about the interval of validity, right? So where the interval is valid, which interval the solution is valid, that's what the interval of validity is. So this is the similar concept, but this is more official or more formal, I would say. Okay, so the function pt and qt must be continuous in that interval, and that interval also must contain the t equals to t0. Then in that case there exists a solution, a function phi t, that satisfies this differential equation. So this is for the linear differential, first order linear differential equation. Okay, now there is a note. What it says is the interval I can be finite or infinite. Sometimes the interval will be infinite, meaning from negative infinity to infinity. That's what it says. Okay, so the alpha and beta can be negative infinity to positive infinity, like that. Okay, so the next theorem is the uniqueness and existence. See, there exists meaning existence, and unique means only one. That's what it means there, right? So we want to define the similar type of theorem for a function that is not linear, meaning if a function cannot be written in that form, then what is the existence and uniqueness theorem for that? Is, so theorem 2.4.2 is let the function f and del f over del y, meaning partial of f with respect to y, partial derivative of f with respect to y, be continuous in some rectangle alpha less than t is less than beta, meaning t is between alpha and beta, and y is between gamma and delta. It is like kind of like, see, this is like t, this is y, right? So this is an interval alpha and beta, this is an interval gamma and delta. So there is somewhere, there is a rectangle there. Okay, suppose t0 is somewhere here, right? So y0 will be somewhere here, right? So that will be y0. So what it says is, let the function f and del f over del y, that is the partial of f with respect to y, be continuous in some rectangle alpha, t between alpha and beta, and y between gamma and delta, containing the point t0, y0. This point will be t0, y0, right? Then in some interval, t0 minus h is less than t0 plus h, in some interval somewhere there, in some interval that contains that t0 and that is included inside alpha and beta, contained in alpha and beta, there is an unique solution, y equals to phi t of the initial value problem, dy over dt equals to function of ty. Okay, so look at this. What is this type of equation? Meaning it may be linear or non-linear or any type of function on the right hand side, because if you solve this for dy over dt, what do you get? You get negative pt times y plus qt, which is a function of t and y, right? So this theorem can be applied for this one as well. But this theorem is more broad, meaning that if the right hand side is linear or non-linear, any type of function on the right hand side works, okay, with the initial condition. This, what we need is, we need the right hand side function and its partial derivative with respect to y, both continuous in some rectangular region. That's what it says. All right, let us see the notes. This theorem is also valid for first order linear ODE, meaning this theorem can be applied for this differential equation as well. Next is, this condition is only sufficient for the existence and uniqueness of the solution of the initial value problem, but not necessary. Okay, so these conditions are not necessary for the existence of the solution. Okay, so but if these conditions are valid, if these conditions are satisfied, then there is a solution. That's what it means. Okay, and the graph of the two solutions cannot intersect each other. So on what, but both of the 2.4.1 and 2.4.2, we talk about the existence and uniqueness, right? There is only one solution. There exists only one solution. So if there are two solutions, they can be parallel, right? So depending on the initial values, or depending on the initial value we pick, the two solutions may be parallel. But if they intersect each other, then the uniqueness will be violated, because they intersect at t0, y0, then there will be two solutions, right? So they cannot intersect. That's what it means. All right. Let us do some examples on how we use these two theorems there. These two theorems are important, okay, guys, for the existence and uniqueness of the solution, because you never know which differential equation has a solution exist and it is unique. Okay, but first of all, you need to check that before you try to solve the equation. If you just try to solve the equation without checking that, then you may have some difficulty, because if the solution does not exist, then you don't want to waste the time by solving it, right? All right, so let us see this example. Without solving, determine an interval in which the solution of t and the parenthesis t minus 4 times y prime plus y equals to 0, y2 equals to 1. And the second problem is natural log of t times y prime plus y equals to cotangent t, where the initial condition is y2 equals to 3. So these are the initial value problem. Let us do the first one. So let me write down the first one in better form. Okay, so number I is, you can write y prime plus 1 over t times t minus 4 times y equals to 0. And what is y2? Y at 2 equals to 1. So this is the given equation in the linear. I just wrote in the standard linear format, right? What is pt? Pt is 1 over t times t minus 4. And what is qt? Qt is 0. Because I divided both sides by that quantity, right? T times t minus 4. And I got the right hand side 0, the left hand side is 1 over t times t minus 4. That's what I did here, right? I divided by that to all of those terms on the left and right. All right. So tell me where the function pt is continuous, because you need to have both pt and qt continuous for the existence and uniqueness, right? So qt is continuous everywhere, right? And how about this pt? Pt is continuous except at t equals to 0 and t equals to 4, right? So pt is continuous. Let me write cont and then exponent and continuous everywhere except t equals to 0 and t equals to 4. Okay, so what does that mean? That means there is 0 and then 4, right? The function is continuous except at these 2 points. But where does the initial value fall? The initial t falls here, right? So t0 is here, meaning that the solution, the existence and uniqueness is guaranteed in this interval. Okay, although the function was continuous, pt was continuous outside that 0, 4, but since the initial value of the initial time falls here between 0 and 4, so the interval of validity, or the required interval is 0 to 4. Okay, so required, you know what, it is better if you write the open thing here. So open 0 and 4, because at 0 and 4 it is not continuous, right? So I write like this. Okay, required interval for the existence and uniqueness, right, is 0 to 4. That's what you see. Let us do second problem. Here you have natural log of t times y prime plus y equals to cotangent t, and then y of 2 equals to 3. That is given. Okay, so how do I write this in the standard linear format? So you write y prime equals to 1 over, let me write y prime plus 1 over natural log of t y, right? I'm dividing both sides by natural log of t, equals to cotangent t divided by natural log of t, and y2 equals to 3. Okay, so let us see where the pt and qt are continuous. So what is pt? Pt is 1 over natural log of t, right? So this function is continuous everywhere if t is greater than 1. If t is greater than 0 and t not equals to 1. Why is that? Natural log of t is defined everywhere for t positive, right? But if t is 1, then this will be 1 over 0, because natural log of 1 is 0, right? So it is continuous every positive values of t, but not 1. Okay, so that's why the pt is continuous. How about qt? Qt is cotangent t over natural log of t. So the denominator has the same thing, right? But for the numerator is continuous everywhere except t equals to, let's say t not equals to n pi, right? Because at n pi, like 0 pi, at 0 cotangent 0 is infinity. Okay, at pi cotangent pi is, let's say n equals to 1. What do you get? If you take n equals to 1, you get t equals to pi. So t equals to pi will give you cotangent pi. Okay, cotangent pi will be cosine pi over sine pi, which is 1 over negative 1 over 0, right? So that is also infinity. So for n is equals to 0, 1, 2, and so on. Okay, and this will exist for negative n values, but this negative n values will give you negative t equals negative n values. Negative n pi will give this negative, but natural log doesn't like the negative values, right? Also, so t equals to 1 is not good too, right? So how do we decide these things? So see, let us draw a line, and then let's say 0 is here, at 0, at 1. Okay, let's say this is pi. Okay, this is, let's say, negative pi, right? So 0, 1, pi. There may be 2 pi, 3 pi, 4 pi, like that, negative pi, and so on. So this function is this function, the whole qt, is continuous only on this side, right? Let me write down that different color. Let me use this different color. This function is continuous on this piece, continuous on this piece, okay, continuous on this piece, and so on. All right, now which piece has the initial condition? It says y2 equals 3, so 2 falls here, right? So t0 equals to 2 falls here. So what is the required interval then? So the answer is I would say 1 through pi, right? Or you can write like 1 is less than let me write 1 is less than t is less than pi, either way. So this would be 0 is less than t is less than 4. Sorry, not pi, 4. Okay, so this is how we find out the interval of validity, or interval where the differential equation has unique solution. So I will take some more examples from this exercise, okay guys? So let us see some more examples. Example number 3 here is the same question. So what you want to do is you want to find the interval where the solution of this exists and is unique. Okay, that's what you want to do. So the previous example were linear differential equation, right? But this is not a linear differential equation. For the non-linear differential equation, you need to use theorem 2.4.2, right? 2.4.2. That's the theorem that you will be using for the existence and uniqueness of this problem. Okay, so what does it say is, if the right hand side function f, this function is f, right? So this function is f, the whole thing is f, and the partial derivative of f both are continuous in an interval, okay, then so let me write down what is the initial value. So initial value is not given for this problem. Then there exists a unique solution in certain interval there, right? So what we need to do basically is we need to look at this. So here, so solution is here. What is f? F is 1 minus t squared minus y squared to the 1/2, right? So what is f sub fy? That is del f over del y. What does that mean? That means you are trying to find out the derivative of this with respect to y, considering all other variable as constant, right? So how that look like? That will look like 1/2, right? And 1 minus t squared minus y squared to the 1/2 minus 1 times the derivative of inside is negative 2y, right? With respect to y. So what do you get then? So f sub y is basically the 1/2 and then 2 will cancel out, right? So what is that? That is 1/2 minus 1 is negative 1/2. That goes to the denominator. We'll make it negative y, right? That's what you get, negative y over 1 minus t squared minus y squared to the 1/2. That power 1/2 is basically the root, right? So the root exists, or this value is defined if the quantity under the root is positive, right? So if this quantity is 0, then this will be not continuous at that point, right? So where does this continuous? Then you can say then by theorem 2.4.2, right? Look at both of these. So the solution exists and unique if this quantity is, when does this root defined? When does, let me write on what that means. That means like negative y over root under 1 minus t squared minus y squared, right? When does this root define is if this quantity is less than 1, right? If t squared plus y squared is greater than 1, then this will be negative under the root, right? If you can write 1 minus t squared minus y squared is greater than 0. Equals to 0 is not possible because it is seen in the denominator, right? So you can write, this can be written as y squared plus t squared is less than 1. So this is the condition, or this is the condition when the solution of the differential equation exists and unique. All right, guys. So let us do the another problem. Dy over dt equals to that quantity, right? That term. So let us say that that is f. F is cotangent t times y over 1 plus y. Okay. So what I want to do here is I want to find out the derivative, partial derivative of this, right? So how that look like is, so here f is that. So how do we find out del f over del y? Is this is considered like a constant because we are trying to find out with respect to y. Okay, so cotangent y is like a constant. Now you need to use the quotient rule, right? Like f over z format. Okay, so 1 times 1 plus y minus y times 1 divided by 1 plus y square, right? What do you get for this? This is 1 plus y minus y, right? So basically you will get cotangent y, cotangent t. Oh, by the way, this is t, right? This is t. This is t. So cotangent t times 1, right? That is just cotangent t, right? And then divide by 1 plus y square, right? From, I'm sorry that the last page was crashed, so that's why I'm just doing it again. So from theorem 2.4.2, the solution of this equation exists and continuous if the function f, that function f, and this function del f over del y, that means the partial derivative of f with respect to y, are both continuous in a certain interval, right? So what are the intervals, or what are the conditions that f and del f over del y are continuous? So you can see that cotangent y is continuous except t is not equals to you say n times y, right? T is not equals to n times y. All right. Sorry, n times pi, not n times y, n times pi, right? Because when n is 0, when n is 1, when n is 0, t will be 0, right? So t will be 0 means cotangent 0 is infinity. So it doesn't like that. When n is 1, -1, 2, -2, all those values, cotangent will give you infinity. So these values are not good value for the cotangent t to be continuous, right? And also this function is not continuous if y is equals to -1, right? And also you can write like this, and thus both f and del f over del y, that is partial derivative of f with respect to y, are continuous for all t except those for which y is not equals to for which y equals to -1, right? And then t equals to n pi, because I said except. So this function, this f and the partial derivative of f with respect to y are continuous everywhere except these points, these values, right? Except the t where y is -1 and t that which is equals to n times pi where n is 0, 1, 2, and so on. Okay, guys. So this says that the because the initial condition is not given, so we cannot find out the interval, specific interval. The question says that verify. By the way, the question says that this was actually question number 12 from the book. Okay, the question says that in each problem between 7 and 12, state where in the ty plane the hypotheses of 2.4.2 are satisfied. So except these points, okay, everywhere the hypotheses of the 2.4.2 are satisfied, meaning that all other points on that plane there exists a unique solution of the differential equation. Okay, so that's what this was question number 12 from the book. So the next I want to do is I want to do question number 14. Okay, question number 14 here from the book, that is example number V. Let me do example V, which is a question number 14 from the book. Okay, so okay, on this example, so there are three parts of the question. Okay, so the first part is verify that y1 equals to 1 minus t and y2 equals to negative 2 t squared over 4 are the solution of this differential equation. Where are the solution valid? So we want to find out that too for both of those. Okay, number B, why the existence of the two solution does not contradict uniqueness part of the solution 2.4.2. Do you remember that when I stated the theorem 2.4.2, I said that if the right hand side function f and the partial derivative of that f with respect to the solution y both are continuous, then there exists an interval around the initial value. Okay, around the initial value where the solution exists, right? But I said that requirement is only the sufficient but not the necessary, meaning that the solution may exist if, even if the right hand side, just the right hand side function is continuous, the solution may exist. Okay, but for the continuity existence, for the uniqueness, not the continuity, for the both existence and uniqueness, you need both of those. Okay, the right hand side and the partial derivative must be continuous. All right, so let us first of all let us do the first part. It says that y1 and y2 both are the solution of this. Let us take y1 equals to 1 minus t. Okay, so solution. So when y1 is 1 minus t, you plug in here, right? And then you should get left side and the right side equal. So what do you get? D over dt 1 minus t equals to negative t plus t square plus 4 times 1 minus t. I'm replacing y by 1 minus t, okay? To the 1/2 divided by what? Divided by 2, right? What do you get? So let me do on the next line there. This is for y1t, okay? So what do you get? You get derivative of 1 is 0, so that will be negative 1. In the left side you get negative 1, on the right side you get negative t plus, what do you get? T square plus 4 minus 4t. So it is t square minus 4t plus 4, right? To the 1/2 over 2. So what do you get? That is negative t, negative 1 equals negative t plus t minus 2 square, but there is an under root, right? So there is an under root of that because root, the exponent 1/2 means under root, right? You can write that way, over 2. What do you get? You get negative 1 equals to negative t plus t minus 2 over 2, right? So that t and t will cancel out, negative t and positive will cancel out, so negative 2 over 2 is negative 1. So left hand side and right hand side equal, meaning y1 equals to 1 minus t is the solution of this. Let's try for y2 equals negative t square over 4. So d over dt negative t square over 4 equals to negative t plus, so let me write root under, that will be easier, t square plus 4 times negative t square over 4, right? That's what I'm replacing y by y2 and divide by 2. So what do you get? You get the derivative of t square is twice t, negative twice t over 4 is negative t over 2, right? Negative 1/2 t. That's the left hand side. Right hand side is negative t plus, is that 4 and 4 will cancel out, so t square minus t square will be 0, right? So divide by 2, right? That is negative t over 2. So you've got left side and right side equal. So hence both t square and both y1 and y2, right? You write y1 and y2 are the solution. Okay, now what we want to do next is basically, so what you want to do next is basically you want to find out what the solution is valid. Find out the interval of validity, or where the solution valid. So what are the conditions for the solution valid, for the validity of the solution? What we need to do is, so we have dy over dt. So we have dy over dt equals to negative t plus, you can write t square plus 4y under the root, right, divide by 2, right? So you can think this as f, right? So this is f. So you need to find out to use the theorem 2.4.2, you need to find out f sub y, right? So what is f sub y? So because f sub y is the derivative of f with respect to y, but taking all other variables constant. So this t is like constant if you are finding the derivative with respect to y. You will see the partial derivative in Calc 3, okay? But this is how we do the partial derivative. So the derivative of negative t is 0, right? So equals to, you can write 1/2, and the derivative of t square plus 4y root under with respect to y, it will be again 1/2, okay? So t square plus 4y to the 1/2 minus 1 is negative 1/2 times 4y times the derivative of the inside. So that will be basically negative y over, you see that, negative y, the derivative of 4y is just 4. So negative 1 over under the root 4, t square plus 4y. That's what you get, okay? So now, to apply the theorem 2.4. Let me write down that, okay? So to apply theorem 2.4.2, we need both f and del f over del y continuous around the point t0 y0, right? What is t0 y0? t0 is 2, y0 is negative 1. It's 2, negative 1. So if both of these solution satisfy, when you replace y by 1 minus t and y by negative t square over 4, then if you find that both y and f of y are continuous around that point, then that will violate theorem 2.4.2, because it says that if both f and f sub y, or the partial derivative of y, partial derivative of f with respect to y, are continuous around that point, then the solution will be unique. But you cannot have both, more than one. Unique means only one, right? You cannot have more than one satisfying that condition. But let us try what happens, okay? So when y equals to 1 minus t, right? So what happens here? When does that both f and f sub y will be continuous? So y will be continuous if t square is greater than 4y or equals to 4y, right? And f sub y is continuous if t square is greater than 4y, right? So t square greater than 4y implies, just plug in that, t square greater than 4 times 1 minus t, right? Because y is 1 minus t. So what do you get? You just bring that everything to the left side. You'll get t square minus 4 plus 4t is greater than 0. You get t square, you can write t minus 2 square is greater than 0, right? So when does this greater than 0? If t is not equals to 2, right? If t is not equals to 2, this is positive, meaning that so this both f and f sub y are continuous except at t equals to 2. Similarly, if you take another function, let y2 equals to negative t square over 4, then you will get that both f and f sub y will be continuous if t is not equals to 0, okay? So you can say that, so you can draw a line, and then there is so positive 2, okay, positive 2 there. So both f and f sub y are continuous except at 2. They are continuous on this side and continuous on this side, but not continuous here, right? So what that means, meaning that it says that y2 equals to -1, right? So meaning that the theorem 2.4.2 says that the both f and del f over del y must be continuous around 2 minus 1. But it is not continuous. Both f and f sub y are not continuous on 2 and then on the left side, because it said that it should be continuous around the initial point, right? Around the initial point. Let's say this is 2 minus 1, right? So 2 minus 1. So it should be continuous around that point. But what we found here is both f and f sub y, if you take y equals to 1 minus t, then both functions are not continuous around 2 and -2, -1, because on the left side they are not continuous for the left of that. Okay, so but if you look at y2, so when y equals to -t square over 4, then t square greater than 4y, that's what we need, right, for this function to be defined, implies t square is greater than 4 times -t square over 4. This is t square is greater than -t square, right? So twice t square is greater than 0. So t square is greater than 0, meaning t should not be equals to 0, right? Otherwise it is continuous everywhere. That means 0 is here, right? And then for this one though, the function y and both f of y, so y and f sub y are continuous everywhere, continuous except t equals to 0, right? But the theorem 2.4.2 says that we need both f and del f over del y, or f sub y, continuous around that. This one is not continuous around that, right? So y equals to 1 minus t is not continuous, but y equals t square over 4 is continuous around 2 -1, right? 2 -1 is here. So for this value of y, both f and f sub y are continuous around the 2 -1. But for this value of y, these both f and del f over del y are not continuous around 2 minus 1. So that's why the theorem 2.4.2 is still valid, although it looks like there are two solutions, but only one solution has the property that is required by theorem 2.4.2, which is the both f and del f over del y are continuous around the initial value 2 and -1, right? So only this solution is the unique solution that satisfies this condition. All right, thank you guys.